So, good morning once again. Today we have discussed how to draw the ILD for the members of the trust. Basically, in ILD, we have considered the two types of trust. One is the through type of trust. Generally, when we move over the river, basically to train, generally the trusses are there in the upward side. That is the through type, and some trusses are deck type. That means the deck vehicle will be moved from the top and the trusses will be at the bottom. And these are the basically two types of truss. And of course there is no large variation, but through type and the deck type, basic difference is the top member. These are the top chord member, that is the upper chord member, and these are the lower chord member. And just change the position of the lower and upper chord member. That means the if the upper chord member is in tension, then in another type, that means the this is the through type. In deck type, it is in compression. Tension converted into compression. That's why. But rest of the diagram, that means the location is same. So let us discuss this truss. This is the truss, through type of truss. Span, generally in case of truss, span is always same, 3 meter, 3 meter, 3 meter, and 3 meter. So total span, that is the distance between the two support, is 12 meter. Okay. And this is U1, U2, U3 that indicate the upper chord member, and L1, L0, L1, L2, L3, L4 or support B, we have considered it is the lower chord member, and these are the inclined members. So here the problem is find out the forces in the or ILD, influence line diagram, for the forces in the member U1, U2. U1, U2, that is the top chord member. L1, L2. L1, L2 is the bottom chord member, and L1, U2 is the diagonal element. Okay. And when we start this, first of all, take the section 1 1. That means we have taken the section in such a way that the whatever the force in the required member should be cut. See the diagram. I have just, yes, sorry. Okay. So this is the diagram which show the section 1 1, which separate the U1, U2, L1, U2, and L1, L2. Okay. And after separation, what happens? We have considered this is the all the after breaking the truss or separate the truss, we can say that there is a development of the forces. So here we have considered, these are the our assumption, all the forces in the member tensile. So I have considered tensile. So this is the section 1 1. This is section 1 1. U1, U2, L1, U2, and L1, L2 separated out. Okay. And then after that, we have applied the unit load. And considering unit load is on the left side and right portion in equilibrium, and then taking the, for the horizontal member, we can take the moment at joint in such a way that moment of other two member will be 0, and moment of required force in the required member should be um, calculated. Okay. Then load will be in the right portion, and we have considered the left portion in equilibrium. Again, we have taken the moment at the same point. And in this way, we can draw the ILD. So let us discuss in detail. So first of all, we can draw the ILD for RA and RB. Actually, this is not required, but for simplification, we can draw the ILD for RA and RB. This is the ILD for RA. See here. This is the support B. This is the support A. For ILD for RA, this is 1, this is 0. And that's why this is 1 to 0. We can draw the straight line, inclined line. All distance is 3 meter, 3 meter, 3 meter, total is 12 meter. That's why this distance is 3. That's why 3 by 12. This is 6 meter, 6 by 12. This is 9 meter, so 9 by 12. And this is 12 meter, so 12 by 12, it is 1. This is the ILD for RA. That means in truss, it is similar to B. There is no issue. Similarly, ILD for RB, again, for RB, we have applied the 1 over the support B and 0 at support A. Join this and then again 3 meter, 6 meter, 9 meter and 12 meter. 3 by 12, 6 by 12, 9 by 12 and 12 by 12. This is the ILD for the RB. Okay. Then this is the ILD for the U1 and U2. How we can find out? Let us discuss. First step is we can draw the ILD for RA and RB. Then second, we have considered the unit load on the left side of the section 1, and right portion in equilibrium. And when we consider the left portion in equilibrium, what is the value of X? What is the range? The range is, we just see, the range is load may be at this point. That means X is equal to 0. We can start from the left to right. And load may be at this point. X is equal to 3 meter. That means 0 and 3 meter is applicable. When we put the load is at this point, it is 6 meter. That is on the right side. But when we consider the load on left side, we have considered X is equal to 0 and X is equal to 3 meter. But when we consider the load on the right portion, in that case, the X is equal to 6 meter, because from left support, we have considered this distance. 6 meter, 9 meter and the 12 meter. And the equilibrium will be considered for the left portion. Okay. So just observe the calculation. It is very simple. There is no integration, derivation, and diagram is also straight line. So no issue. So U1, U2, for U1, U2, we have taken the moment at U2. Why we have taken the moment at U2? Because I want force in the member U1, U2, and that's why we have taken the moment at L1. When I have taken the moment at L1, what happened? Force in the member L1, U2, which we have already break after taking the section 1 pass from the same point, and L1 L2 also pass from same point. And that's why moment of these two forces, because we have considered the right portion in equilibrium, moment of this force and moment of this force passing through L1, that's why 0, and moment of this U1 U2 is equal to, can I say, this force multiplied by perpendicular distance, that is 4 meter. Okay, and this side only RB is there. Okay, so RB multiplied by, we can see that the 9. RB multiplied by 9, and this U2, U1, U2 multiplied by 4 in the opposite direction or same direction, same direction. It will move in this direction. This RB also move in the same direction. So we get force in the member U1, U2 is equal to minus, because both will be plus, is equal to 0, and that's why we get, see here, force in the member U1, U2, sorry, here, yes, just a minute. Actually, we have taken the moment at L1. We have taken the moment at L1, not U2. This is L1. Yes, L1. So is equal to 0. 4, that is the height is 4 meter multiplied by U1, U2. Anti-clockwise, that's why minus. So minus 9 multiplied by RB is equal to 0. So we get force in member U1, U2 is equal to minus 9 by 4 multiplied by RB. Here RB related with the vertical increment or ILD for the RB. But this equation is applicable if X is equal to 0 and X is equal to 3 meter. Okay. Similarly, now we have considered the unit load on the right side. We have considered X is equal to 6 meter, 9 meter and 12 meter, and consider left portion in equilibrium. Repeat the same procedure. We have taken the moment at the same point, L1, not U2. Okay, so just again see the figure. Yes, this is the figure. So we have considered load is at L2, L3, L4 like that, and the moment is taken at L1. Again, can I say U1, U2, course in member U1, U2 multiplied by this height 4 meter and RA multiplied by 3 because we have taken the moment at this point in the same direction, clockwise direction. That's why both are positive. Therefore, we get the equation. Yes, we get the equation force in member U1, U2 is equal to minus 3 by 4 multiplied by RA. Okay. So, after this, we can tabulate the result. Better way, either we can use the direct ILD for RA and RB or we can tabulate the result so that it will be more convenient. So, distance 0, 3, 6 meter, 9 meter and 12 meter because total span is 12 meter from A to B. ILD increment for RA 1, then 9 by 12, 6 by 12, 3 by 12 and 0. And for the RB 0, 3 by 12, 6 by 12, 9 by 12 and 1. Okay, these are the vertical increment from the ILD. And first equation is applicable for the 0 and 3. That's why I have already written minus 9 by 4 into RB. So here we have just put the value of RB, that is this one. First is 0, that's why this value is 0, and second value is 3 by 12. So we have put here RV is equal to 3 by 12. 9 by 4 into 3 by 12, we get minus 9 divided by 16. That means the compressive. Similarly, for the second one, the equation is, this is the equation, minus 3 RA divided by 4. Generally, we can put the value of RA for 6 meter, it is 6 by 12. So 3 by 4 into 6 by 12, it is minus 6 by 16. And for second one, 3 by 12, here R is equal to 3 by 12, its value is minus 3 by 16. And when I put at 12 meter, its value is 0, that's why it is 0. So 0 to minus 9 by 16, then minus 6 by 16, minus 3 by 16 and 0. So we get the ILD for U1, U2. Now this is the ILD for U1, U2. 9 by 12, 6 by, 9 by 16, 6 by 16, 3 by 16 and 0, 0. This is minus, that means the compressive. This is the ILD for the top chord member U1, U2. Okay. Similarly, for the bottom chord member, which is tensile, again, we have considered the same concept. We have used the same section 1, 1. Okay, but here again after we need this one, and when we can take the moment at u2, what happened when I have taken the moment at u2, force in the moment of this force u1 u2 passing through the same point, that's why 0. Moment of this diagonal member passing through u2, that's why 0. And moment of this l1 l2 is force in member l1 l2 multiplied by height in this direction, and rb in the opposite direction, rb multiplied by 6. That gives, but for the we can say that load on the x is equal to 0 and x is equal to 3, we have considered this portion in equilibrium. And when we have considered load on the right side, that is 6 meter, 9 meter and 12 meter, this portion is considered in equilibrium. Again we have taken the moment at the same point. Again force this member and this member pass from the same point, that's why moment of this will be 0, and moment of l1 l2 in this direction, that is the anti-clockwise direction, multiplied by 4 is equal to ra multiplied by this distance, that is 6. Again we get the another equation. Okay, and in this way we can draw the ILD for, this is positive, first is negative, and for that bottom chord member it is positive, 6 by 16, 12 by 16, 6 by 16 and 0. This is the ILD for the L1 L2. Okay, so this is the calculation, we have just go through the calculation. Yes, here consider the left portion in equilibrium, bottom chord member here. Actually, it is U2, not U2, not L1. U2. Okay. Then minus 4 into L1, L2 plus 6 into RB, we get the force in member. But this is applicable if x is equal to 0 and x is equal to 3 meter. Similarly, consider the unit load on the right side, left portion in equilibrium. And again, we can take the moment at the same point. So this is again U2, right? So we get the force. And again, tabulate the result. This is ILD for RA, similar to previous one, ILD for RB. And this is force in the member. Here we have written the these values and we get 0 minus, sorry, it is minus, not minus, it is plus. And these values are, I have just show you, 6 by 16, 12 by 16. These values are 6 by 16, 12 by 16, again 6 by 16, and then 0. So the ILD is positive, that is tensile. This is the ILD for the L1, L2, 6 by 16, 12 by 16, and 6 by 16. Okay. Similarly, for the diagonal element, again, we have considered the section 1, 1. For diagonal element, here it is observed that this is the diagonal element L1, U2. So when I have taken the section and this is RB and RA, which is vertical. So is it possible to resolve in vertical direction? Yes. If we know the value of theta, angle is known to you, this diagonal element can be resolved in vertical direction. So we can say that the value of this member is resolved and we get the vertical component. Okay, this is theta, and this theta is known because tan theta is equal to 4 divided by 3. We get the value of theta. That's why there is no issue. This theta and this is also theta, alternate angles. Okay, so this will be resolved. So force in the member, we can say that L1 U2 multiplied by sine theta in downward direction, so minus, and this is RB in the upward direction, plus, is equal to 0, and we get the value of L1 U2. Similarly, when we have considered load on the right side, that means the load is here, here, or here. Okay, unit load is in this direction, and consider the left portion in equilibrium. Again, this member is resolved like this. This is also force in the member L1 U2 into sine theta, L1 U2 sine theta. Okay, and this in the same direction, RA, and this in the same direction, but here this is in opposite direction. That's why this will be positive and this will be negative. So let us check the calculation and then show the ILD. So here, now here we have considered summation Fy is equal to 0 in y direction. Force in member U1, U2 in downward direction, that's why minus into sine theta, plus RB is equal to 0. So force in member L1, U2 is equal to minus RB divided by sine theta. But this is applicable if x is equal to 0, x is equal to 3 meter. Okay. Similarly, we have considered the load on the right side and left portion in equilibrium. In that case, we get the another equation, force in member L1 U2 sine theta, that is in the upward direction, right? And RA is also in the upward direction, though both are positive. That's why we get the minus RA divided by sine theta. Now again tabulate the result. For tabulation, these three columns are same. in ILD for RA, ILD for RB, distance, and we have just changed the value depending on the equation. This equation we have put here in the remark, and for x is equal to 0, definitely it is 0, and for we can say that the x is equal to 3 meter, it is 1 by 4 sine theta positive. And for second, it is minus, that's why minus 1 by 2 sine theta, minus 1 by 4 sine theta, and 0. That means for diagonal section, it is divided by sine theta and partly positive, partly negative. Now, this is the influence line diagram for the diagonal member. 0 plus 1 by 4 sine theta. Second section we have considered, then minus 1 by 2 sine theta, minus 1 by 4 sine theta. That's why this will be like this, partly positive, partly negative. Okay. So in this way, we can draw the ILD for the top chord member, bottom chord member, and the diagonal member. Similarly, we can find out the ILD for the vertical element. And for vertical element, definitely it is not possible to take the section in vertical direction, but in the inclined direction. For example, here, if I want the force in this member, say U1 and L1, this member, in that case, what happens? We can just take the section like this. We can take the section like this, cut the member, this vertical member, horizontal member, and this member, and then we can take the summation Fy is equal to 0, because these both are the horizontal element. Only vertical component and this vertical component are this in picture, and we can find out the ILD for the vertical element, right? Okay, so you better understand this ILD for the beam, ILD for the truss. Actually, it is very simple. If you do some practice over the different trusses, then you can already uh, get the correct result. Or ILD for the positive, that means the tensile member, it is on the upward side above the reference line, and compression, it is below the reference line. And for diagonal element and for vertical element, it is always 1 divided by some constant into sine theta. Of course, for diagonal, it is partly positive, partly negative, and for vertical member, it may be negative, it may be positive. Thank you very much. Have a nice day. Best of luck.